All right, welcome everyone to the group session focusing on slurry and mix design and troubleshooting. If you have any questions, please enter them in the chat box on pathwell.com. All questions will be answered at the end of each presenter's session. We have 3 presenters for the session. Pat Denny has worked in the asphalt emulsion industry for 35 years as a plant operator, laboratory technician, and field engineer. He currently served as the microsurfacing manager for Arkemi Road Science. He is responsible for mix design, formulation of emulsion, and aiding customers with any troubleshooting issues related to microsurfacing and slurry surfacing. Tim O'Connell worked for Koch Refining as a plant operator from 1979 to 1983. He then served as a laboratory special project manager and Northern Region technical manager with Koch Materials from 1983 to 1992. From there, he became the Western Region technical manager until 2006. From 2006 to 2008, Tim worked as a formulation lab leader in Tulsa, Oklahoma from SEM Materials. In 2008, Tim began his role as a formulation lab leader where he supported the asphalt and asphalt emulsion products in the U.S. until 2011 for Road Science. Since 2011, Tim has been with Ingevity with Tulsa, Oklahoma Laboratory working on the development and support of asphalt emulsion and mastic technology. Richard Wenth has become in the micro surfacing and slurry seal industry for 39 years, 25 years with Bolu Construction and 5 years with Road Science, in the last 9 years as a technical service engineer with Ingevity. I leave it up to you, Pat.
Thank you, Kate. Good afternoon, everyone. I'm glad you're here with us today. I hope that this training today will be informative and that you appreciate the information that you get today from not only myself, but also Tim and Rich. So let's go ahead and get started. We're going to talk about microsurfacing today and some of the different items, different parts. It's split out in 3 different sections. First section is for design and the design process from aggregate testing to the final report. Then we'll talk a little bit about the bulking effect or the quantitative effects of moisture on the weight of aggregate. And then I want to talk a little bit, just briefly, about stockpile gradation tolerance and what it means. The key components of a quality microsurfacing mix are polymer modified emulsified asphalt or an emulsion, dense graded 100% crushed aggregate, mineral filler, typically Portland cement or hydrated lime, and also a control additive. The goals of microsurfacing and slurry surfacing mix designs are to determine if the component materials are compatible and also to determine if the combination of materials that provides the best overall performance in the field. When we get an aggregate in for microsurfacing or slurry seal, first thing we need to do is check the gradation and sand equivalency. If either one of those fails, it automatically triggers a retest of a second pail of the material that came in, and then we'll determine from there whether we move forward or not doing the rest of the testing. We also test methylene blue value and report that, and we'll also do the unit weight or the bulking effect and report that. Everything passes. Let's say everything passes on the aggregate, so we're going to move for making emulsions. I like to start in my design process using 4 corners, especially what I call 4 corners, especially if we're looking at working with a new emulsifier or an unfamiliar aggregate. What I mean by 4 corners is that the emulsifier will be a high and low value, the soap solution will be at a high and a low value, and then we also want to make sure that the emulsion we produce fits the specification that we're working with. After we get emulsions produced, we'll start doing our trial mixtures. During the trial mixtures, we're going to look at the effects of pH that the pH has on curing and on mixing. We're also going to look at the mineral filler and the effects of mixing and curing, so we'll adjust the mineral filler up or down up and down to see whether it provides better curing and better mixing. The emulsion formulation will, we're going to look at the different effects of the formulation. So whether it's a high chem load, low chem load. So we're going to evaluate. We'll record the mix times for that, and then through all that, we're going to try and optimize that formulation. Then we're also going to evaluate the optimum moisture content, and we're going to do that based off of consistency, mix time, curing at room temperature. After we get our hand mixes completed, then we'll move to the performance testing. And you can see on the right, those are the list of the tests that we run. And I'll talk about those a little bit as we go through this presentation. And then finally, we'll write a report and submit it for review before sending it off to our customers. Trial mixes. So we start out adding materials into our bowl the same way that they would be added into the pug mill on a micro surfacing machine. So you aggregate, then mineral filler, water, control additive, then emulsion. And we want to mix that material at room temperature. And you can see the on the bottom of the second picture there at room temperature, specifications or the guidelines are typically around 120 seconds at room temperature, and then 35 seconds at 100 degrees Fahrenheit. And that's all materials being at 100 degrees Fahrenheit. But what we primarily try to do is we want to meet customer expectations. So we may be looking at a higher mix time or quicker cure time or whatever. So we're evaluating all those issues when we're doing the hand mixes. ISSA TB100 is a test method for wet track abrasion of slurry surfacing systems, and the purpose of it is to establish minimum asphalt content for the slurry surfacing system, and it also provides a determination of long-term moisture susceptibility after 6-day soak. On the left, you can see this is how we make the specimen. It's basically just a large hand mix, and we pour it in the mold and we screed it across that mold there onto some tar paper. Then it's cured for a period of time according to specification. Afterwards, if it's going to be for a 6-day soak specimen, it'll go into a water bath at 77 degrees for 6 days. If it's only a 1-hour soak, it'll go into a water bath at 77 degrees for 1 hour before testing. On the right, the picture on the right, you see the technician there. He's loaded the specimen into the Hobart mixer with some clamps that are clamping that specimen down. And then there's a weighted abrasion head that runs across that or around that specimen for a specified amount of time. It kind of depends on which mixer you're using. Is at the time, it could be anywhere from 5 minutes to 6 minutes, 45 seconds, depending on the mixer. Afterwards, you dry it and then weigh it again, and then you calculate what your grams per square foot loss is. Now for 6-day soak wet track, it's 75 grams per square foot. And for a 1-hour soak, it's 50 grams per square foot, and that's for microsurfacing. For slurry seal, it's 75 grams per square foot for a 1-hour soak on slurry. When we make the specimens for wet track, we'll also start making our specimens for the Schultz, Breuer, and Ruck procedure, typically because both of those samples, all those samples have to soak for 6 days before we test them. The purpose of the Schultz, Breuer, and Ruck covers the determination of compatibility between aggregate fines of a specific gradation and emulsified asphalt residue, in which that asphalt emulsified residue it stays the same no matter what the aggregate is. It's always the same percentage. It's 8.125% plus or minus 0.1. It also provides a rating system for abrasion loss, integrity, adhesion characteristics, and the specified aggregate fines and emulsified asphalt residue. You can see here the 4 stages: absorption, abrasion, the Ruck integrity. and adhesion. At stages 2 through 4, each stage earns a point rating, and it can only pass with a minimum of 11 points. We make the specimens in a small mold, compact those at 140 degrees Fahrenheit, let them cure out, soak them for 6 days. After 6 days in a water bath, we pull them out, weigh them up, put them in this tube on the left, full with 750 milliliters of water, and then put them in the machine on the right to allow that to abrade through the water for 3 hours. After that 3-hour period, we weigh it again, take it out, weigh it again, starch rated, surface dry, and then put it in a beaker filled with water and let it come to boil. Then we put it in the pill into the basket and let it boil for 30 minutes. After 30 minutes, we take it out of that basket and let it cool for a few minutes so that we can handle it. Then we weigh the largest cohesive mass again, and then we apply based off of that weight. There's a calculation that takes place, and then you can determine what your rating is for that different stage as well. The next test, while those, I guess I'll go back, while the wet tracks and the Schultz broilers are in the water bath, they're soaking for 6 days. We'll continue working on the design, doing other testing. These tests do not take near as long for curing and for testing as those others. So we can do these and get the design done quicker instead of waiting for any test to finish. So this is a test method for the measurement of excess asphalt through the use of a loaded wheel tester and sand adhesion. The LWT is intended to compact the fine aggregate bituminous mixtures such as slurry seal by means of a loaded rubber tire reciprocating wheel, and you'll see that in a minute. The test may be used for design purpose to establish maximum limits of asphalt to avoid severe asphalt flushing under heavy traffic loads. So if you remember, the wet track was for establishing a minimum asphalt, and the sand adhesion is to help establish the upper limits. On the left is the picture of the technician adding the specimen to the loaded wheel tester. You see the weights on top. That whole apparatus from the wheel with the weights weighs 125 pounds. The specimen is loaded into this machine and then allowed 1,000 cycles over that specimen at 125 pounds. You can see in this picture that there's three specimens there. One's before the test, one is after it's been tested through 1,000 cycles, and the third one is after it's gone through this is the sand adhesion. Now, the sand adhesion comes in after we've done 1,000 cycles. We add hot sand onto the specimen, we place a mold over that, add the hot sand, put a little metal plate over the top of that, and allow that machine to run over that specimen again at 100 cycles. Pull everything off, tap the specimen, trying to get all the loose sand off the specimen as we can, and then weigh it again. We weighed it before, we weigh it after, and then we'll get a maximum or a grams per square foot of sand adhesion. The maximum it can be is 50 grams per square foot. And I apologize, I forgot to put that on this slide. So, but again, the maximum is 50 grams per square foot. Along with the sand adhesion, we also make specimens for testing the stability and the resistance to compaction. And we do that by measuring lateral and vertical displacement of that multi-layered fine aggregate cold mix. Basically, it's the same type of sample, but the difference is the curing for this specimen. It's a little longer cure for this specimen before we actually do the test. And what we'll do, it runs through the same number of cycles, 1,000 cycles. But prior to that, well, before I get too far ahead, the purpose is to measure the amount of compaction or displacement characteristics of the multi-layered, dense graded, fine aggregate cold mixes, such as slurry seal or a cold microasphalt bituminous surfaces, microsurfacing, under simulated rolling traffic compaction. So as I said, 1,000 cycles. Before we put it subjected to 1,000 cycles, we're going to measure that specimen in 3 different areas along the center of the specimen, and get an average. That'll average out, and then we do the same thing after the test. And what we're doing is we're measuring that kind of lateral displacement, how it moves apart or sideways, shoving, if you will. It's not really shoving, but it does displace a little bit. The maximum for that is a 5% lateral displacement. We'll do the same for vertical displacement, or the compaction of the material. We'll measure it before, we'll measure it after. It can be a maximum typically of around 10%. We also measure specific gravity. Some specifications will state that the specific gravity for the specimen should be done prior to lateral displacement. Some will say after it's been compacted in the or after the test has been run. But the maximum specific gravity is 2.1. The test method for determining the set and cure development of the slurry surfacing systems by cohesion tester. It's used to determine the initial set and cure development of slurry surfacing systems as a function of torque over time. This quantifies the time required before a slurry surfacing system may be subjected to straight rolling traffic. You see on the left the apparatus that's loaded with a specimen, and our technician has a torque meter at the top. The foot has been applied, has a rubber foot that applies to the surface at 200 psi, and then he rotates that torque meter 90 degrees within 1 second, and we'll get a reading off of that torque meter of for 30 minutes. The specification is typically for a quick set or quick traffic systems. It's 12 kilogram centimeters at 30 minutes. And for quick traffic, it would be 20 kilogram centimeters at 60 minutes. Final test would be the wet stripping test. Typically what this is when I've made my hand mixes, after they've cured for 24 hours, I'll pull about 10 grams off of the specimen and drop it in boiling water. You can see on the picture on the left, the beaker with the water. It has a shelf that keeps the specimen off the bottom of the beaker. And it's allowed to boil for 3 minutes. There are boiling tests that are modified and they will boil for longer. But this particular test for ISIS ATV14 is a 3-minute boil test. After it's through boiling, you decant the water and pour the specimen out onto a paper towel and let it set for 24 hours. Then basically it's a visual test. You come back and you look at the material and determine with your eye as best you can the percent retained coating on the aggregate. And if it's 90% or greater, it's considered satisfactory. Between 75 and 90 is marginal, and less than 75 is unsatisfactory. Now, personally, I've never seen one of these fail, but not to say that it won't happen, but I've never seen one fail. For the report, we're going to list the recommended emulsion content on the report, the residual binder content, recommended mineral filler content, and all 3 of those will have tolerances or a range that they need to kind of stay in based off of the design guideline. We'll list the aggregate test results, the gradation, the sand equivalency, methylene blue, bulking effect. And then we're also going to list the mix time and the effects of mineral filler on the mix time and set time, or the cure rate. And then we'll also list the performance test results that we have, that we performed. All right, we're going to move on to section 2, the quantitative effects of moisture on weight of aggregate. This just kind of shows you how we do it. You can tell we start with dry material. You can tell it's dry if you look on the slide, the picture on the left. You can see the dust coming up. So you start out dry. That is, on the left has the mold, a collar, and then the aggregate being poured into the mold. It has to be around 2 inches above that mold. So afterwards, we'll pull that collar off the top and then strike it off even with the mold with a straight edge, and then we'll weigh it. We'll do that, and then we'll add 1%. We'll add moisture to the aggregate at 1% increments. Make sure we stir that around really well to get the moisture good and dispersed throughout the whole entire sample. Then we'll do the same thing again. We'll add it to the mold, strike it off, and then weigh it again. This is a sample being weighed. You can see that weighs 5,770.8 grams. The mold itself weighs 4,000 something, 4,500 something grams. But on the next slide, I'll show you the table of the bulking effect. You see on the graph at the top, it shows the line that as we added water, the weight, or the weight went down in pounds per cubic foot. So our pounds per cubic foot went down as we added water. And the reason for that is because that aggregate defines, when you add water, it swells and it takes up space. It causes those fines to kind of swell up, and that creates less space for, or less room for the aggregate to fill the mold. So you'll have less aggregate being added. So you can see that as we went from 0 to 5%, the dry weight went down, and at 5%, actually it bumped back up. So, and the reason for that is that at 4%, that was our maximum amount of absorption for that aggregate for this test. And then after, at 5%, what that's telling us is that now we're weighing aggregate, the water absorbed by the aggregate, and now we have excess water on the outside of the aggregate that we're also weighing. So the weight will bump back up a little bit. So 4% was our max amount on the bulking effect where it changed. So we didn't go any further after that, after 5%. Now I want to relate this to field. So imagine, if you will, that all my weights, they are all the same as they were on the previous slide in the table below, but now they're changed from a weight per cubic foot to weight in pounds. And the reason for that is I want to relate bulking effect to the field. And if you look at it from the standpoint of just dry weight, which everything is based on dry weight, if you can imagine, if you will, that you have a gate setting at 4 inches, your stockpile has 3% moisture in it. You do all your calculations, your calibrations, and so you've got everything set. Your emulsion content, you've got everything set where you need it. So your emulsion content is going to be at 12% with a 7.8% residual asphalt in your mix. But what happens if your stockpile dries out and you're not keeping track of what's happening with your stockpile moisture? So it's important that you continue to check those moisture. So If it dries out and it goes down from 3% to 2%, now you have the weight that is going through that gate, instead of being 1,220.8 pounds, now it's 1,303.5 pounds. The amount of emulsion that's going into that mix, and I forgot to say this the first time, at 3%, when your gate was at 4 inches, the amount of emulsion going into the mix was 146 pounds, which equates out to 12% at 65 residual, 7.8% residue in the mix. Now the material's dried out. You've got 1,303.5 pounds of aggregate going through that gate. Nothing else has changed. You haven't changed gate settings, or you haven't made any changes to the computer. Everything is still the same. Is still running the same, except now the aggregate that's going through that gate opening weighs more than what it did. So with the same amount of emulsion being pumped into the mix with 146 pounds at 1,303.5 pounds of aggregate, now your emulsion content has gone down to 11.2%. And then at 65 residue, now you're at 7.3% residual asphalt in your mix. Conversely, if you get a rainstorm and your moisture content in your stockpile goes up, and let's say it goes up to 4%. So you can see by the chart down below that at 4%, now the weight of aggregate that's flowing through that opening is 1,158.2 pounds. You're still pumping 146 pounds of emulsion into it. So what does that do to your emulsion content? It goes up because you've got less aggregate. So now instead of 12% emulsion, you're running 12.6% emulsion is what it calculates out to, or 8.2% residual asphalt. So now your asphalt contents go up. So just remember that to continue to check your moisture content in your stockpile, make adjustments if you need to, because you'll want to make sure that when you set your gate and everything for a certain percentage of residual asphalt in the mix, that you maintain that consistency regardless of the moisture content that's in the stockpile. So you'll need to make adjustments. Stockpile gradation tolerance. And also I have some poll questions that I entered. So if you get an opportunity, go answer those poll questions. I really would appreciate that. And they deal with the bulking effect and the stockpile tolerance. Stockpile tolerance, as described in A143 of ISSA, is the gradation of the aggregate stockpile shall not vary by more than the stockpile tolerance from the mixed design gradation. That's important, mixed design gradation, while also remaining within the specification gradation band, and that's even more important. And also the percentage of aggregate passing any two successive sieves shall not change from one end of the specified range to the other end. So let's talk about the aggregate gradation. This is an actual gradation that we ran in our lab, and you can see that on the left-hand side are the sieves, and then percent passing as received. We also included percent passing with the mineral filler in the aggregate, and then the specifications, and then the stockpile tolerance. So on the stockpile tolerance, I don't know if I have a. This is your stockpile tolerance right here. This is set forth by ISSA. These are ISSA numbers. Agencies may specify something a little bit different from this. I've seen it done, but what this says is that these numbers to the side of that on the left-hand side, 67 to 77%, means that you cannot go. What the heck happened here? Oh man! All right, quit touching stuff, Pat. Sorry about this, guys. Anyway, you cannot go outside of that stockpile tolerance range. So this is your gradation. These are as your materials being delivered to the job. So this is on the left or on the right, the minimum and maximum. That's where you need to stay within, and now that is related back to the gradation. Let me go to there. This is the gradation. This right here. This is the job design gradation right here. Everything, these numbers here are based off of these numbers here, not these numbers in the specification. Okay. Let me explain a little further. We had some confusion this year that the explanation that they were giving to certain folks, they misunderstood what stockpile tolerance was. They thought the stockpile tolerance was based off of the specification and not the job mix formula. Okay, so this is the gradation that we had for the design. This is what they had was being delivered to their stockpile, and they were saying that it was still within tolerance because it was within this percentage of these numbers here. Well, that's not true, and they didn't know that, didn't understand that at the time. Because if you go back to the first slide, it has to be based off of job mix formula gradation, and it has to be within the specification. So if you'll notice on here, the stockpile tolerance does not go below the specification. Okay, but these gradations are out of specification because they don't meet the spec, but they're also not within stockpile tolerance because they do not meet the specification. I hope that's clear. I hope I didn't muddy the water anymore. If you have any questions on that, feel free to ask me, and I'll try and explain it a little better. Anyway, that is the end of my presentation. And you can see on this last slide, there's my email. So if anyone wants to reach me at some point in time, if you have any further questions, feel free to go ahead and reach out. And with that, I will yield back to Kate if there's any questions.
All right. We have no questions as of yet. So I'm going to go ahead and thank you, Pat, for your presentation. Please